So let's take a look at how we can get some characteristics of quadratics just from looking at a graph. So you see all this information over here and you're thinking, oh goodness, that's a lot. But it's pretty straightforward. We're kind of making the next logical step from just when you started learning to factor these, to solve these, to graphing these. And now we want to kind of go a little bit opposite to think logically and say, okay, well, what can I extract if I give you the graph? And we could also give you the equation and expect the same results. We can actually go a step further and give you ask for the x-intercept if you have the equation, because here you can kind of see we can't really guess what the zeros are for this. But anyway, so with this, let's go ahead and let's take a dive and see what we can get from this graph. So the domain, if you remember, is all the possible x values of a function. Okay, in this case, I should have put little arrows up here because it goes on forever and ever, right? So quadratics, they go on infinitely in the x direction in either way for our quadratics when they're pointing upwards. In future courses, you'll look at quadratics that open sideways, but we're not worried about those now. Solely these ones go from left to right for infinity in both ways. So from negative infinity to a positive infinity. That would be the domain, okay? And for the range, if you remember, the range is just the possible y values, okay? So if we look here, and when we're doing y values, and when we're doing domains like this, in set interval, we always go from least to greatest. So from smallest to largest, okay? So from range, what's the smallest possible y value that we have? If you'll notice, it doesn't cross this. It does not get any smaller than -3. This is kind of like the minimum point for that. So we start at -3, and it's inclusive, okay? When we do interval notation, we can either put a parentheses or a little square bracket. If it's a parentheses, that means we do not include it. So we put a parentheses around infinity because you can't include infinity. You don't really know we don't know what infinity is, right? And that seems weird, but it's an abstract, number for our purposes. But you can't put an inclusive sign on it because you can include it. It's not on the graph. So for the range, we can put a -3. That's part of this graph, okay? I didn't mean to get philosophical on either, but it's important to remember. So -3, and then where does it go? It just continues to go up forever and ever and ever. So for that one, it would just be a positive infinity. Okay, parentheses. But and that's pretty much it for the range. For the vertex, we already have part of it. It's the very for quadratics, it's the max or the min. That's going to give us the y value at least of the vertex for the upward or downward facing quadratics. So for the vertex, where are we at? Right here, we go -1 down 3. -1 down 3. Okay, and there's the vertex. So for the axis of symmetry, that is basically a line. It's going to be the equation of a line, and sometimes they'll tell you explicitly, hey, what's the equation of the line that represents the axis of symmetry? In this case, if you look at it, it's kind of like the line that we can draw straight down, and it'll go, it'll cut this parabola in half, this quadratic equation in half, right? And if you look, I'll give you a tip, a nice little hint. The axis of symmetry, when we're dealing with vertical quadratics, which is our sole focus in whatever course you're most likely in, if it's an algebra course, something like that, the equation is going to be x equals whatever the x coordinate of the vertex is. In this case, x equals -1. So x equals -1, that's going to be a vertical line at -1. Pretend that's a straight line. Sorry about that. But it'll look like this. And if you look, it cuts this in half. If you were to fold it over, they would fold directly on top of each other. Okay? So that's the main idea with the axis of symmetry. We can get it right from the vertex. It's very convenient. So for the y-intercept, that's just where does it cross the y-axis. And here, it's a nice, when you get graphs like these and they ask you for these particular values, like something that's on the graph, like the vertex or the intercept, they're most likely not going to be like, it's going to be something like 1.33, that'd be too much. You can't really guess that. Sometimes you will get like maybe 1.5s, but it'll be a lot more zoomed in than this, and it'll be pretty straightforward. Okay. So with these ones, we're giving you whole numbers because you need them. You can't really eyeball, a 1.2, right? You can, but it's too much of a guess. So with this, the y-intercept, it crosses at -1. So you can put sometimes -1. I like to put them in coordinate form, just because. So for the interval of increase, now we're thinking for the interval of increase, we read graphs. This is important to remember. We read graphs from left to right. So as we're going from left to right, what's happening? Well, we're going down, we're going down, we're going down, and we stop. We stop right here abruptly at this vertex, and then we start going up. So we start going up. There's a little point at this vertex. We're neither increasing or decreasing. That's an important concept to remember, okay? At the vertex, we are neither increasing nor decreasing. We kind of stop for it. Kind of think of a ball. If it was flipped, it would be like a ball at the top of the hill. It just stopped for a second, and then it's going to start rolling back. So when it's upside down, it's just think of a, I think I said this in another video, it kind of falls down and then it just miraculously shoots back up. But for the increase, it starts at -1 and it continues to positive infinity. And it's not inclusive because, again, we can't be increasing and decreasing at the same time. And I'll show you that in this next one where we're decreasing. As we go from left to right, we're going down, we're going down, we're going down, and we stop. We stop at -1. And if you're thinking, okay, well, it's going to be -1 to negative infinity. But remember, we go from the least amount to the greatest. So we're starting, it's decreasing from negative infinity all the way up to -1. And that's where it stops, and it transitions to this part, and then it starts to increase. So it's decreasing, decreasing from negative infinity all the way up to -1, stop, and then we're starting to increase, okay? So it's neither increasing or decreasing at the vertex of a quadratic. A very important point to remember, for the average rate of change between 2 points is the function value of the first minus the function value of the second over just the difference of the two x coordinates, okay? So for this first one, b is 0, a is -1, okay? So what's the function value at 0? So actually, let me rewrite this. So let's put our actual coordinates in. F of 0 minus f of -1 all over, let me scroll down a little bit because we're kind of running out of room. There we go. F of -1 over 0 minus -1. So what's our function value at 0? If you look up here, when x is 0, we get what? We get -1, okay? Minus, and then what's f of -1? F of -1, when x is -1, we get -3. So minus -3. All over 0 minus -1. 0 minus -1. So you can kind of see why negative arithmetic is important here, because if you don't know how to subtract or add negatives, you could be in trouble. So with this -1 minus -3, think of the two negatives, they cancel out. So -1 plus 3, we get, let me change the color here. Let's go. There we go. Positive 2 over 0 minus -1, so 0 plus 1 all over 1. And that just equals 2. And another way that you can look at this is the average rate of change between 2 points is the same numerical value as the slope of the line that connects those 2 points. So if you look, if I connected these 2 points and I asked you, what's the slope of this line? It goes up 2 over 1. Hey, look at that. That's what we got. So something to note there, the average rate of change between 2 points is going to be the same value. It's going to have the same value as the slope of the line that connects those 2 points, okay? And that's pretty much, that's all they really ask you of these. Again, we could take it a step further if we give you an equation, an actual maybe, x squared plus 2x plus, something like that, and you can factor it and figure out one extra point. You can find out the x-intercepts as well, which we call the zeros or the roots also, okay? So let's take a look at another one. So with this, the domain, what do we have? The domain just comes up, and again, I wish I put these arrows up here. It goes from negative infinity all the way to positive infinity. The x values, it doesn't cease to exist for the x values. The x values always, any x value that I could put in to a quadratic, there's always going to be a corresponding y value, okay? Now for the range, what do you think? Does this same thing hold true for the range? Did we go from negative infinity to positive infinity? And hopefully you're thinking, I don't think so, because it stops right there. It doesn't go any less than 1, right? So our lowest value is going to be 1, inclusive. We include it on there because it's part of the graph. It's on the graph. And then we just go upwards just like the other one, forever and ever and ever. So with that, it'd be positive infinity. In the vertex, that's pretty straightforward, right? We get a 2, 1. 2, 1. The axis of symmetry, we just look at this, and like I said, it's just the x equals whatever the x coordinate of the vertex is, and it would be a vertical line just like this. Okay, and the y-intercept, where does it cross the y-axis? I kind of crossed over it a little bit, but it's right up there, right there. So it crosses, the y-intercept is where it crosses the y-axis, so we would write it as, let me get a different color, write it as 0, positive 5, okay? Interval of increase, again, we're reading from left to right. Obviously, as we go from left to right, it's decreasing, decreasing. It stops right here. So 2, automatically that you should think, okay, it's going to start increasing at 2, and then where's it going to increase to? Well, positive infinity. These quadratics have a nice a nice pattern, a nice, I don't want to say symmetry, but they have a good pattern that you can kind of predict what they're going to do. Let's try that again. Infinity. It's not too good. Sorry. So for the interval of decrease, what are we doing? So as you can see, we're decreasing. So we must have been decreasing forever as we're going from left to right before we even got to this point. So it's kind of like negative infinity all the way up to a positive 2. And again, we're not including these 2's because it can't be increasing and decreasing at the same time. It doesn't work like that. Okay, so what about let me come back. There we go. The average rate of change from 2 to 4. So this is going to look like f of 4 minus f of 2 all over 4 minus 2. So what's f of 4? What's our function value at 4? If you look up here, we get a 5. That equals 5 minus, and what's the function value at 2? Well, we know that because that's the vertex. That's 1. And if you didn't, again, you could still just look at the graph and say, oh, there you go, it's 1. But with that, and then we get 4 minus 2. So we get 4 over 2, which is just 2. And this would be the same value as the line that's a bad line, sorry about that. That would be the same value as the slope of the line that connects these 2 points. And if you look, let's double check. Let's see what we get. If I go up, we choose that green color. If I go up 1, 2, 3, 4, and then over 2. Hey, 4 over 2. Perfect. So we got that. And again, they're not always going to be whole numbers like this, but usually when you're working with graphs, they kind of have to be because they don't expect you're not going to be able to eyeball, again, like 1.333, right? We're not calculators and we don't pretend to be. So with this, we'll try one more. Wanted to switch it up on you and get a downward facing one. So the domain, do you think that changes? Do the x values change because we're going down? No, they do not. It still is negative infinity to positive infinity. So hopefully you've recognized the pattern here. We have negative infinity to positive infinity. Okay. Now what about the range? The range, what do you think? Maybe you think, okay, you think it doesn't go past 3, so maybe 3, but it's going down. He's trying to trick me. Maybe it's 3 to negative infinity, right? If you put 3 to negative infinity, you're very, very close. But remember, we do the lowest values first because we're going from left to right. In this case, we're going kind of down to up. So we're going negative infinity to positive 3, inclusive on the 3. Okay. And for the vertex, what do you think? It's pretty straightforward, right? It's just right there. Negative 1, 3. Negative 1, 3. Axis of symmetry, again, we just pluck that little x value, and it's going to be x equals that. That's the equation of the line that represents the axis of symmetry. For the y-intercept, do the same thing. Well, not the same thing, but the same thing as the other two. Where does it cross the y-axis? And it crosses right there at negative 1. So I'll put negative 1, and we'll put it in coordinate form. Boom, we got that. Interval of increase. Now as we're going from left to right, we're increasing, right? So we're changing up a little bit from the other two. We're increasing, and then we stop here. So it's increasing from negative infinity all the way up to this point here, which is negative 1. Because remember, for the intervals of increase and decrease, we're using the x values, okay? Okay, what about decreasing? We know if it stops increasing here, unless we have ones where we go like that, these crazy quadratics, which I don't think you'll see until a later course. For our purposes, these ones, it's going to increase to a point and then decrease, or it'll decrease to a point and then increase. Okay, so if we know that it's stopping to increase here, then it's going to start decreasing there. In so many words. Okay, so there we go. Negative 1. Let me write that again. There we go. Negative 1 to positive infinity, and that's where it's decreasing. It's rolling down this hill forever and ever. And what about the average rate of change between negative 1 and 0? So the x value is negative 1 and 0. So we're going to have f of 0. Actually, let me go back to the red color. I like the red color. I don't write fully in it because it gets a little bit too much on the eyes, I feel like. So let's say we have f of 0 minus f of negative 1 all over 0 minus negative 1. A lot of negatives again, and that's okay. So f of 0, we get negative 1 minus, and what's f of negative 1? Positive 3. So our function value at when x is negative 1 is positive 3, and then over 0 minus negative 1, which is the same thing. These cancel out. We get 0 plus 1. We get a positive 1. And negative 1 minus 3, what is that? That's negative 4 over 1, which just simplifies to negative 4. And let's double check. Let's see what the slope of the line that connects this seemingly straight line that's supposed to be straight. It looks like a quadratic itself. But let's see what the slope of that line is. So we go down, we start up here, we go down 1, 2, 3, 4. That's a horrible line. And then we go right 1. So we go down 4, right 1, which is the same thing as negative 4, which is this right here, literally negative 4 over 1. And there we go. So I wanted to get that idea that the average rate of change between 2 points is the same value, again, as the slope of the line that would connect those 2 points. But other than that, that's pretty much it. I hope you found this video helpful. Until next time, this is Justin with Top Tier Math.